So we'll cover the last module of this course, that is partial differential equations. Okay. So after this module, maybe we will revisit. I will revisit the course. What more important things we need to learn, and we can learn that during that time. Okay. But I saved these for the last. Okay, because I knew that first I should cover the most important things, and then we will cover to this partial differential equations. So anyway, partial differential equation sounds very complex, but we will start with very highly intuitive things. Okay, we'll recapitulate what are the partial differential equations, how to solve it. As usual, you don't need to know anything mathematical. Okay, you have to just deal with numbers in numerical methods. Okay, you have to just deal with numbers, add them, multiply them, and get the next value based on the past value. Okay, that's what numerical methods we have been doing so far since the last 2 semesters. Okay. Okay. So partial differential equations can arise in lot of fields, like in the study of applied mathematics, like fluid dynamics, heat transfer, boundary layer flow, quantum mechanics, and many like electromagnetic theories and all those things. And only a few of these equations, like partial differential equations, have analytical solutions. Okay, and most of them don't have analytical solutions, and those equations, those PDE equations who have analytical solutions, those often require highly advanced mathematical topics. Okay, so of all numerical methods available for the solution of PDE, the method of finite difference is usually used. Method of finite differences. Okay, so it is just like the slope. Given 2 points, x1, y1, x2, y2. What's the slope between the lines? M equals to the slope equals to y2 minus y1 by x2 minus x1. So similar kind of concept we will be using. Okay, similar kind of concept we'll be using. Okay, fine. So a general linear partial differential equation, okay, of second order, and two independent variables. So they usually take this form. So I'm writing in general. So this is the second partial derivative, like dou to u by dou x2, and axy is a general function being multiplied. Okay. Then you have bx comma y, where you have mixed partial derivatives, like dou to u by dou x dou y, plus cx comma y, dou to u by dou y2. Okay. This is with respect to the second variable y. Okay. Then you have something mixed, which you can write as f of x, y, u, or dou u by dou x, dou u by dou y. All those terms can be incorporated in f. They can be incorporated in f. Okay. Maybe there is a y term, maybe there is a u term, maybe there is a mix of u, x, du by dx. All those terms are belonging to f equal to 0. Now this is a general linear PDE of second order with two independent variables x and y. So u is a function of x and y. U is a function of x and y, and it follows this rule of PDE. Okay, our job is to find the function u. Okay, our job is to find the function u, and you know, most of you have already taken courses in their bachelors. You know that you can find analytical solutions for this, but it is very difficult, requires advanced mathematical techniques. Now the idea is how we can solve it using numerical methods. Okay, so I hope you already know that this PDEs, any kind of PDE can be classified into three types. They can be classified into elliptic, parabolic, hyperbolic. So you know this PDE is of three types: elliptic, parabolic, and hyperbolic. Okay. So how many of you know about this elliptic parabolic parabolic hyperbolic? How many of you know? Might be in bachelors. Okay. Okay. So it depends on this coefficients. It depends on this coefficient A, B, C, and F. Okay. So if it is elliptic if b square minus 4ac is less than 0. It is like treating as a discriminant. Okay, b square minus 4ac is less than 0. It is parabolic if b square minus 4ac is equal to 0. It is hyperbolic if b square minus 4ac is greater than 0. Okay. So my question next to you is, I will give you some equations. You have to tell me whether it is elliptic, parabolic, or hyperbolic. Okay. So in this course, we will learn about parabolic equations. Okay. Elliptic also we can learn, but it is a bit more complicated. We'll skip it. We'll just know the minimum things, okay, to solve the numerical methods. Okay. Fine. So classify this equation. Classify this equation as elliptic, parabolic, or hyperbolic. Which kind of equation is this? Also this. First equation is yes, first equation is, what is this equation? What's the type? This column, what kind of equation is this? Why? Yeah. So equal to 0. Okay. So it is parabolic. I hope many of you got this idea. You can find b square minus 4ac and it turned out to be 0. Yes. Second equation. You want to this column, which equation it is? First one. Why? What is b? Leah will tell. What is b in the first equation? 4 b square. B square 4 square minus 4 into a is 1, c is 4. Can you see? You have to identify a, b, c using looking into this equation, comparing this equation. Comparing this equation, you have to tell me. So what is the second equation? What is the second? X squared d2 dou to u by dou x2 plus this. What kind of type of equation is this? No, check again. What is b here? B is 0. A is x square. C is 1 minus y square. Is it? So b square minus 4ac is minus 4 x square into 1 minus y square. Okay. Yeah, I forgot to give one condition. The condition is x can be in this length. X can be from minus infinity to infinity. X can vary from minus infinity to infinity. Y can vary from minus 1 to 1. Can you now use this constraint here to think what should be the sign of b square minus 4ac? So since it is x square is positive, 1 minus y square will always be positive because y is in between minus 1 to 1. Since y is in between minus 1 to 1, 1 minus y square is positive, right? Yes. So this is positive, x square is always positive. Okay. So what you get, b square minus 4ac will be less than 0. B square minus 4ac is less than 0. If it is b square minus 4ac is less than 0, what kind of equation it is? Yes, now you have found the type of this PDE. Okay. So first equation you saw an example of parabolic PDE. Second example you saw the example of elliptic PDEs. Okay. Fine. So like this it can come. Okay. Similarly, let us turn to elliptic equations. So elliptic PDEs. Okay. So there are two famous equations so far in scientific literature. Okay, one is Laplace equations. Another is Poisson equations. Okay. So what are Laplace equations? Laplace equations are of the form del to u equal to 0. Grad to u. What is grad? U is a function of x and y. So grad is equivalent to dou by dou x2. Dou by dou 2. Yeah, x2 or plus dou 2 by dou y2. This is the grad 2. So when you apply to u, it becomes dou 2u by dou x2 plus dou 2u by dou y2 equal to 0. So if you see this kind of equation, it is known as Laplace equations. Okay. What is Poisson equation? Poisson equation will be dou 2u equals to some f of x comma y. If it is 0, it is Laplace. If it is right hand side, some function is there, it is a Poisson equation. Okay. So therefore, dou 2u by dou x2 plus dou 2u by dou y2 equals to f of x comma y. If you have this kind of equation, it is known as Poisson equations. If you have Laplace equation, it should be del to u equal to 0. Okay. So these are the two types of problems. These you find in many flow equations, steady state flow, when water or any fluid flows. Okay. For those fluid dynamics, you can see these equations mostly in electro problems like yeah, most in electrical problems where you have voltage, power, and all those things. They usually use the Laplace equations because electricity or the current deals with many other parameters. Okay? And Poisson equation generally arise in many of these fluid mechanics. Okay. So basically, in any other master course you go in mathematics or any other university, they have a specific course on fluid dynamics where they read about these partial differential equations, and many they dedicate a whole semester on this. And there are also computational techniques, computational fluid dynamics, but we have suppressed this course by not including that course, but we have added one module here. Okay, that is partial differential equations. Okay, so just as a brief, you can know about it. So the problem is in these elliptic kind of PDEs, you basically see that u is a function of x and y. U is a function of x and y. So x can vary, y can vary, and depending on that, u will vary. So therefore, you always have a region. In PDEs, therefore, you always discuss regions. What is the region? What is the region? That means you will deal with something like x, y, and there will be a reason. There will be a closed region, some closed region like this. Okay. The bounding curve is C, and this is the region R. This is the region. So your solutions are usually dealt with in region. Like in this region, I want to solve the PDE. Okay. So the solution of this equation is a function u of x comma y, and that solution is satisfied at every point in this region. The solution of the PDE will be satisfied. Suppose del to u equal to, suppose, 5x plus 6y squared. Like this it is behaving. Like this your fluid flow is behaving. Okay. So at this point, at each of these black points I am marking here, it should satisfy this equation, this PDE equation. Okay. Fine. So this is the Laplace equation. So what we do is usually we take a mesh. What we do is usually we take a mesh of this. This is how mesh occurs. And therefore, the idea of PD is simple in numerical methods. You divide them into mesh, and based on these points, based on these green points which will be given to you, you find the subsequent points. You find what is this point, you find what is this point, this point, computationally, as a hope that you have found the solution over this region R. Okay, that's the idea. Okay, that's what we will be doing in this course. Okay. Now let us come back. Let's go to the new slide. Okay. So we have, suppose, this Laplace equation del 2u equal to 0. What it looks like? Dou 2u by dou x2 plus dou 2u by dou y2. Okay. So how can you, you wrote this equation. How you can convert this into numerical methods? Mr. Sajid, how you will convert this into a numerical methods? You only. How? What should I write next? Huh. So here, basically, you have to use finite difference schemes. So to proceed further, to proceed further, we use finite difference schemes. Finite difference schemes. Okay, finite difference schemes which will discretize our system. So that should be the first step. First you discretize, and then you suppose apply initial case. How without discretizing you can apply initial case? Okay. So first you have to discretize the system, because numerical methods always is of the form xn plus 1 as if some function of xn. Yes. So these are discrete. Step after step it goes. Okay. So how we can discretize it? So you have to apply something known as a second order discretization. Okay. So I hope like you can apply something like this. Dou u by dou x, as I told you, it is just like a derivative. So you can treat it as a slope form. What is slope form? Ui plus 1 minus ui divided by xi plus 1 minus xi. The 2-point slope form, you remember. So this is like u at xi plus 1, this is u at xi. And xi plus 1 minus xi. Generally we take equal step size. So therefore, ui plus 1 minus ui divided by h. This is a particular kind of scheme. Okay. Now this is a forward scheme where you deal with I plus 1. Okay. Similarly, there is a backward scheme also where I plus 1 you don't deal, you deal with I minus 1. Okay. So similarly, there is something related for the second order derivative. For the second order derivative dou 2u by dou x2, you have something like this. ui minus 1 comma j minus 2u I comma j plus u I plus 1 comma j divided by h squared. Okay. This might appear complicated, but it is simple enough. How it is simple enough? You can think of dividing the region in the xy plane into ith location on x-axis, jth indices on y-axis. Okay. So then you can divide it. You can think of it as like, yes, like if you are here, I comma j, if you are at this location in your grid, this complex mathematical notation will be clear once I show one graph. Okay. You are supposed at I comma j. What is the next step on the right? I plus 1 comma j. What is the next step on the left? I minus 1 comma j. Okay. What is the top condition? I j plus 1. What is the below condition? I j minus 1. This all you have to know about. You have to visualize it like this. Okay. So how it happened? If you are taking the second order partial derivative at that point, you have to take this point. You have to take this point. You have to take minus 2 times this point, then plus this point. So you're taking the neighboring points in order to find the second order partial derivative. Okay, you're taking the nearby points on that x direction to find the second order partial derivative. Now let us come to dou 2y by dou y2. So what it should be? Since it is varying with respect to x, the first index changed. I minus 1, I plus 1. J is fixed. Can you see? J is fixed. Now when you are taking derivative with respect to y, dou 2u by dou y2, what it should be? ui. Now j will change. J minus 1 minus 2uij plus ui j plus 1 divided by same like h square. So now you can see that if you take this, then it is just like, say, maybe what other things are involved. If you are considering the second derivative, you have to consider that point. Fine, that point itself. Then what you have to consider? J minus 1, this point you have to consider. Then I j plus 1, this point you have to consider. So I hope that is clear. If you are considering the partial derivative with respect to x, the x index will change nearby, left to right. If you are taking with respect to y, the y coordinate will change according to the neighbor. See this for yellow, you see this yellow one, see this green one. Okay. So these are very nice to understand the visualization. These are normally referred to as stencils. Okay, these are like stencils. Where to go, which one to take. Okay, fine. Now, can you put this into this main equation? Can you put this into this main equation? 1. If you put this into main equation, what you get? Can you solve it? What you get? Tell. Put that and tell. What is your aim? Yeah, but what should be your aim? You are doing it, but what should be your aim? Our aim is to find ui comma j. What is our aim? Our aim to find ui comma j based on nearby values, isn't it? To find ui comma j based on nearby values, isn't it? Now you put the dou 2u by dou x2 plus dou 2u by dou y2, what you get? Equal to what? You will get 1 by h square times ui minus 1 comma j from here, this equation minus 2ui comma j. This one you will get, no? Isn't it? So the 1 by h square is always positive. So therefore it won't be 0. So only this guy will be 0. Since this guy is not 0, so only chance is this guy to be 0. This guy to be 0. Now if this guy can be 0, what it should bring you? Can we make uij common? Can we make uij on the left hand side and put all of them on the right hand side? If you do that, what you get? You will get 1 by 4. 1 by 4 times, because minus 2 uij minus 2 uij. So 4ij will go on that side. you divide by 4, okay, making left to uij. So uij is 1 by 4 times what? Ui minus 1 comma j plus ui plus 1 comma j plus ui j minus 1 ui j plus 1. Now what is important about this? The importance about this is, if you want to solve if you want to solve this, if you want to find the value of I comma j, then you need the help of I minus 1 comma j, I plus 1 comma j, I j plus 1, and I j minus 1, and take the average of all these 4 nearby quantities, 1 by 4th of 4 quantities. So in order to find this middle point, you have to take the average of the left, right, top, bottom. Okay. So this is something nice, and this is usually referred to as standard, like, yes, standard 5-point formula. This is referred to as standard 5-point formula. Why? Because 1, 2, 3, 4, and 5. 5 points are involved in this computation. This is known as standard 5-point formula. Okay, fine. Now there can be a similar formula also. There can be a similar formula to this. Can anyone be creative? Can you be creative? Instead of these 4 points, top, right, left, bottom, left, right, top, bottom, instead of that, we can take other 4 points also. Those points can be, any ideas? Those points are here, but you are not able to see them. They're here. How about you take 1 point here, 1 point here, 1 point here? These can be diagonals, no? They can be diagonals, isn't it? So what can be this point? Yeah. Yes, tell. I minus 1 comma j plus 1. What is this coordinate? I plus 1 comma j plus 1. This coordinate? I minus 1 comma j minus 1. This coordinate? I minus 1. I plus 1 comma j plus 1. Yes. J minus 1. Good. So these are the 4 points. Now you can write a similar formula based on this. You can write a similar formula based on this. So based on the blue points, how you can write? Uij equals to 1 by 4th of u, take this point, d1, d2, d3, d4. Can you tell me those points? Ui minus 1 comma j plus 1 plus ui plus 1 comma j plus 1 plus ui plus 1 j minus 1 ui minus 1 j minus 1. Can you see this? This is based on the diagonal points. This is based on the diagonal points. So where it went? I want to highlight it. So this is based on these diagonal points. Based on these diagonal points. Okay. So I hope this is clear. Now, since you're considering these diagonal points, this is known as something like diagonal 5-point formula. Okay. Okay. Fine. So this is known as a diagonal 5-point formula, but it is often less accurate. You can show it via error analysis that this is less accurate than the standard 5-point formula. Okay. But it is often less accurate than standard 5-point formula. Okay. Fine. I hope this is clear. So yes, based on these values, we will derive two more methods. We will revisit two more methods which you dealt with in last semester. Those are, those are, there will be methods similar you visited in last semester. What are those methods? What are those methods? Oh, yeah. So there are two methods that you have already visited in last semester. Those are Jacobi method and Gauss-Seidel method. So they will appear here again. They are so nice that they come to linear equations, solving linear equations. They also come in PDs. Okay. So you know, in Jacobi method, what you do, you take the usual format, but in Gauss-Seidel, you take the most recent value. Okay, most recent value, and Gauss-Seidel method is more accurate than the Jacobi. Yes. Yes. So you can improve their accuracy by using these two methods. So how Jacobi and Gauss-Seidel method looks like? Okay. So here we will illustrate them. So Jacobi method, how it looks like. Jacobi method. So often you see this is the 5-point formula. This is the 5-point formula you have seen so far, but you have to keep on iterating so that you converge to the final solution. Yes. So you need to iterate. But here I never told you about iteration. What you did so far, you took the left point, you took the right point, you took the top, you took the bottom, you took the average. That is not iteration. Where I should put the iterations? In as I told, in numerical method, there should be a future value which should depend on the past to iterate. That's how you get to the solution. Yes. So how you have to iterate it? So therefore, this formula, what I wrote, here, and here. Okay. This formula, what I wrote here and here, they have to be modified for iteration schemes. So Jacobi method will look exactly like the standard 5-point formula, but with iteration. That is, instead of uij, I have to write n plus 1. I have to write n plus 1. Uij n plus 1, that should depend on the past values. So how the past values? 1/4 of, same as this first equation, u I minus 1 comma j at nth step plus u I plus 1 comma j at nth step plus u I j minus 1 at all at nth step, all at nth step. This is what you call the Jacobi method. Okay, but how Gauss-Seidel method looks like? Gauss-Seidel method will look exactly like this, but you know that this method takes the most recent update. This method takes the most recent update. How it looks like? U I j n plus 1, okay, is equal to what? 1/4 of u I minus 1 j. Fine. Let us write all these values first. Then I will show you regarding the iterates. Uij plus 1, fine. But what should be the iterates? What should be the iterates? So basically there will be two changes. Okay. Here you have n plus 1th. In both of them you have the most recent form, n plus 1. You take the value at the most recent state, n plus 1. Whereas for others it is the same, n. This is Gauss-Seidel. Observe here you took all n. But here you are taking I minus 1 j and ij plus 1. Those terms will only be n plus 1, the most recent updates. Okay. Other terms will be the same, nth terms. So like that you did for Gauss-Seidel in the previous semester. You took the most recent available value in your iteration scheme. So therefore, this is how Gauss-Seidel will be more efficient than the Jacobi method. Okay. Fine. So I think we should do a problem. Yeah. So you can see, I will revisit you. So this is how it is. Like you have x and y here, x and y, and you want to find the solution here. You want to find the solution here. So you depend on the previous values. You depend on this. You depend on the right. You depend on the top. Depend on the bottom. This is how this grid is. After you find this green point, you will move to the next green point. You will move to this point. You will move to this point. This point. So like that, you will keep on computing the solutions. So you will find the solution across the whole domain. Okay, that's how the numerical method scheme is. Okay, and this is the closed region where your solution U is defined. Okay, fine. Let us go to this. And this is how I mentioned you about the diagonal 5-point formula and all those things. Okay, so here you see this is the standard 5-point formula. To find the solution here, it depends on this guy, left, right, top, bottom. Okay, but this is standard 5-point. But on the right hand side, this is diagonal 5-point. This is diagonal 5-point. How? From this point, you compute this diagonally. I hope you understood the difference between. Okay. So this is just graphical representations of all these things. So yeah, maybe we will solve this problem first. Okay. So we'll solve this problem first. Yeah. So this is the question. You see this question, okay? So this is the question. This is the Laplace equation, okay? This is the question actually. This is the grid given to you. Your job is to find U1 to U9. Your job is to find U1 to U9. How you will find it? How many of you think that it is very hard? Very hard. That is the issue. Like it might be very hard, but the moment I will break it in front of you, it will be very easy. Okay. So see that in front of this guy, in front of AB, this is A, this is B. You flip the chocolate bar. Think of this as chocolate bar. Okay. You flip the chocolate bar upside down. So can you see that 500 is here, 500 is here, 1000 is here, 1000 is here, 500 is here, 500 is here. 1000, 1000, 1000, 1000. Now, if values are distributed that symmetrically, what it should tell you? That it should tell you, it should ring in your mind that it is symmetrical. It is symmetrical across AB, isn't it? It is symmetrical across AB. How many of you understood this? It is symmetrical across AB. Now let us see to the next guy, that is CD. Now let us fold the chocolate bar across this vertical line. Now see that 500 is here, 500 is here. Okay. 500 is here, 500 is here. 1000, 2000, 1000, 1000, 2000. So it is symmetrical. So it is symmetrical across CD also. It is symmetrical across CD also. Yes. Now, what we can take advantage of this symmetry? How we can take advantage of symmetry? See, if this value equals to this value, along this value should be equal to this value. Are you getting the idea? U1 should also be equal to U3. U1 should also be equal to U3. U4 should be equal to U6. U7 should be equal to U9. Yes. Now, when you fold across AB, let us mark with pink. 1000 is equal to 1000. 1000 is equal to 1000. Then U1 should equal to U7. U1 should equal to U7. U3 should equal to U9. Are you getting the idea? That's how you can solve it. And then you use the final diagonal 5-point formula. If you can find these formulas, you can find U5. Okay. And of course, U2 is also equal to U8. Across AB if you fold. Yes. So you can find the values. You can find the values, isn't it? Now, let us write it mathematically. If it is symmetrical across AB, what should be the condition? This guy gives what condition? Tell me. If it is symmetrical across AB, U1 should be equal to U7, comma, U2 equals to U8, comma, U3 equals to U9. Yes. Now let us take this guy. Symmetrically across CD, what should it be? U1 equals to U3, yes. Then U4 equal to U6. U4 equal to U6. Then U7 equals to U9. Yes. So how can we solve this? Anyone? Okay, this is what we got. Like, if we can find some values, then like dominoes, you can find all other values. Okay. But we have to start from somewhere. From where we have to start? From where we should start? Any ideas? From where we should start it? Yes. From where we should start it? See, you have to just find some initial values, then keep on iterating. Then keep on iterating. Here we don't have initial guess. Here we don't have initial guess. We have to find initial guess. How you can find initial guess? So what is the idea? The idea is you have to find the U1 to U9. That is your job. Your job is to find U1, U2 up to U9. But none of the initial values is being given to you. Only boundary values are given to you. Boundary initial conditions are given to you. How you will find? So the idea is you have to find U1 to U9 for initial value. What kind of method you use? You use diagonal 5-point, you use standard 5-point. However, you find the values of U1 to U9 initially, then keep on iterating. So that it will converge to the actual solution. Yes. So how can we find it? Can we find, so which one you should consider first? You tell me. Which one you should consider first? Okay. This is initial guess. This might seem random, but it is a good initial guess. I will go with U5, the center guy. U5. U5 I can find by finding. This is U5. I will treat this guy here and here. I will take the average of those because I cannot take average of U4, U6, U2, U8. I don't know the values. So as a starting guess, this is a guess. It's a good guess. Okay. It's a good, see, 2000, however, U4 will not be 20 or 0. It won't be that difference. It will be just 200, 300 difference. Think of it as a heat flow. Think of it as a metal plate. If this guy is 2000 kelvins or 2000 degree, then this guy will not be 10 degrees. This guy will be also very close to that magnitude. Okay. So therefore, U5 is 1 by 4 times this guy 2000 plus this guy 1000. This is initial guess. Plus 1000 here below. Then on the side, here 2000, I think. What should be this value? $2,500. 1,500. 1,500. After you find U5, what you should find next? You got U5, initial value. What should you find next? Think. Think. It is the game of thinking. How about U1? Can we find U1? See U1. Can we find U1? Can we find U1? How? Hmm. Yes, yes, exactly. That is diagonal. Diagonal you are seeing. So you see diagonal. You see the diagonal. We want to find U1. We want to find U1. So you see the diagonal. You see the diagonal. If you see the diagonal, what value you are getting? So you can take the average of 0, 1000, 2000 and U5, which you just calculated. U5 you just calculated. So can we write U1? Yeah. U1 equals to 1 by 4 of 0 plus 1000 plus 2000 plus U5. That is 1 by 4 times 3000 plus 1500. U5 you already obtained. U5 you already obtained. What should be it? 4500. 1126. After that, what you have to compute? What you should compute? You should compute those values which should not be equal to, see, U1, you know, U1 is equal to U7, U1 is equal to U3. So you should not compute U3 and U7 because you already know that they are equal to U1. You are unnecessarily doing the calculation. Okay, got the idea? U1 you computed, but you should not compute U7 and U3. It's already equal to U1. Okay, so U7, U3 you don't need to compute. Then remaining are there. Yeah, which one you should compute? Yes, let us see U2. How we can compute U2? Why we can compute U2? Yeah, why we can compute U2? How yeah, okay, you told U2. How we will compute U2? You should tell that also. U1 U1 we got. U3 will be the same. U5 we got. 1000 we got. Yes, fine, done. So like that you have to see it very carefully. So what you need to do in order to compute U3, sorry, U2, you have to see this guy, which you already know. U1 you already knew. U3 already know because U1 is equal to U3. 1000 you already know. U5 you already know. I hope this is clear. So what values I should write? U2 equal to 1 by 4 of U1 plus 1000 plus U5 plus U3. So that should be equal to 1 by 4 of U1 is how much? U1 is same as, oh yeah, 1125 plus 1000 plus U5 is how much? 1500 plus U3 is same as U1, 1125. How much is this? Should be an integer only. Should be an integer, I think. 1187.5. What else is remaining? So U2 if you found out, that means U8 and U6 you already found out. So you have to only find U9 also you found out. U1 equal to U3, U3 equal to U9. What else is remaining? I think we found everything. No? Because U7 is U9, U1 equal to U7. So everything is computed. Just by computing, do we need to find any other thing? Yes, exactly. U4 has not been found. Yes, can we find U4? How can we find U4? I think it is trivial. It is trivial. What you need to do? You just need to take this. Okay. How you will get the formula now? Can you write the formula for this? U4 equals to 1 by 4 times 2000 plus U1 plus U7 plus U5 what should be the value? 1 by 4 times 2000 plus u1 is, u7 is, u5 is, how much you are getting this? 1424, 1437.5. So you got every value. Can you see that based on this simple technique, you were able to find all the unknowns just by your visualization. Okay. So what should be the next step? What should be the next step? U5, did we calculate correctly? U5. U5. Okay. Now what should be the next step? This is just the initial values. These are just the initial values. You have to iterate your scheme. Isn't it? Fine. So how we shall iterate? Let us use Jacobi method. We will use Jacobi method now. Later we can use Gauss-Seidel. Okay. So using Jacobi method, can we find using Jacobi method? Now these are all initial guess you have. What should be U5? So U5, maybe I will start with U1. U1 of n plus 1 should be, U1 of n plus 1 should be equal to 1 by 4th. Anyone? U1 of n plus 1. I think now we can use our normal 5-point formula, standard 5-point formula. So what should be? It should be 1 by 4, 1000 plus, tell me. 1000 plus U4, right? U4 of n plus, on that side, U2 of n plus 500. Able to understand? You do. Start. Yeah. You can compute now. What you got? U1 n plus 1? 1031.5. So U2 of n plus 1 should be, U2 of n plus 1 should be 1 by 4 of, huh? Okay, thanks. 1 by 4 of 1000 plus U2n plus the right hand side U3n plus U5n. Is it correct? Is this U2? What? Good. Like this, you have to correct me if I'm wrong. Yes. So what should it be? 1 by 4 of 1000 plus, what is U1n? What is U3n? Same. What is U5n? What should be the value? 1187.5. Yes. What should be U3? U1 is equal to U3. So you don't have to compute. What else you have to compute? U4. U4n plus 1. 1 by 4 of U1, U7, U5. U1, U7, U5. U1, U7, U5. 2000, right? U1, U7, U5. N step. What should be the value? 1 by 4 of 2000 plus U1n. What is U1n? U7, 1125. U1 is equal to U7, right? Then 1500. What should be the value? 14. Yeah. Okay. Can you compute like this? The other three? I think other two are there. Yes, what else is remaining? What else is remaining? U1, U2, U4 you computed. U5 we have to compute, no? U5 of n plus 1. That is you this guy. Yeah. Adhyans and Saji will tell. U5 n plus 1 is equal to 1 by 4 of tell. Hmm. Tell. U2 plus U4 plus U6 plus U8 divided by 4. Yeah. U2 plus U4 plus U6 plus U8. Is it correct? No. Has to be nth iterate. Isn't it? So what should be the value? 1 by 4 of what should be? This value total. 1187.5 plus hmm? Hmm. U6. How much? 1. So this is the second iteration. Okay. Like that you have to compute till you converge. 3, 4 iteration. Okay. So this is the Jacobi method for solving the PDE. Okay. Okay. This one is your assignment. Okay. This one is your assignment using Gauss-Seidel and Jacobi. You have to, this is the assignment, you have to solve it using Gauss-Seidel and Jacobi method. Okay. Yes, Gauss-Seidel and Jacobi. First you do with Gauss-Seidel, then you do with Jacobi. Okay. I hope you have clicked, no? You clicked. Hmm? Okay. Yes. Okay. Yeah. So I hope so. What kind of PDE you solved just right now? Anyone? What kind of PDE you solved right now? What kind of PDE? Hmm? What kind of PDE we solved? This column. Hmm? Elliptic PDE. What kind of PDE we solved right now? That column. What kind of PDE? Elliptic PDE. See the question. What we solved? What kind of PDE we solved? You developed that formula from Laplace, right? Del to u equal to 0, dou to u by dou x2 plus dou to u by dou y2 equal to 0. Then you solved using stencils. You arrived at the standard 5-point formula, diagonal 5-point formula, right? That is for Laplace equation, right? So where we solved elliptic. Okay. So, okay, that's fine. So now you know how to solve Laplace equations. Okay. Not much different will be there when you try to solve elliptic equations. Okay, elliptic equations almost similar. Just that del to u equal to 0 won't be there. Equal to some non-zero quantity will be. So elliptic and parabolic you now know. Okay, fine. So another parabolic PDE which we want to solve right now is based on only one variable. Okay, not depending on any other variable. Okay, so that is like heat equation. Okay, heat equation. The idea is like simple. You have like a bar 0 to L. You heat it. Like here one temperature is there, here another temperature is there. How the heat flows throughout the bar. That means if we want to measure the temperature at some points or randomly at the bar, can we find the temperatures of the bar at some points? So this is done by using the heat equation. How the heat equation looks like? Heat equation looks like this. The rate of change of temperature with respect to time. You know that this bar after 10-20 minutes will be at a normal temperature of 37 degrees Celsius. Yes, that is a normal room temperature. Yes. So it should with time. It should be with time. Like you want to compute at which time instant from the experiment which we conduct now. You heated it, you kept it. You want to observe the heat or the temperature after 5 seconds, after 10 seconds, after 20 minutes. So therefore, with respect to T, small t is the time, capital T is the temperature. Okay. Dou capital T by dou T equals to alpha dou 2t by dou x2. So T varies with both x and time. The temperature here will vary with respect to x. Okay, suppose here you added 30 degrees Celsius, here you added 40 degrees Celsius, then somewhere here it can be 35, 37, like this. Yes, it will flow like this, right? So therefore, T, the temperature varies with respect to the locations, that is x. But at the same time, temperature varies with respect to time also. Okay. After 10 seconds, temperature might decrease. After 20 seconds, temperature might decrease. Yes. So temperature is a function of both x and t. So when you have more than one variable, you cannot do ordinary differential equations. Therefore, you have to move to partial differential. Yes. If temperature was only varying with respect to x, then this is sufficient, dt by dx. But since temperature is varying with respect to x and t, therefore you need dou t by dou x, dou t by dou t. I hope this is clear. If you have if a variable depends on more than one variable, it is like partial differential equations. If it is varying with respect to only one variable, then dt by dx is the same as dou t by dx. Dou x, no difference. Okay. I hope that is clear. So basically you have a length that is x. So you have this constraint. X is in between 0 to L, where L is usually the length of your domain. L is basically the length of your domain. Okay. Now how to solve this? How to solve this PDE? Okay. How to solve this PDE? So when we will be solving this PDE, it will be having two batches. That means from 0 to L, you divide into equal intervals, that is x1, x2, so on till xn. Yes, xn minus 1, sorry. This can be, yeah, x0 to xn, yes. Then this is a time t equal to 0. It also varies with respect to time, right? It also varies with respect to time. These are the temperatures at these points from 0 to L. Now for time equal to 1 second, you will have another batch. For time t equal to 2 seconds, you will have another batch. Yes. Similarly, for time t equals to t seconds, you will have another batch. Depends how much you want to compute. Later, you have all these data points. You can later plot the temperature T versus time T as a heat map that we will see in Python. You can plot it as a heat map. All these data points. Okay, if you want a good heat map, you have to discretize these value very close to each other, very close to each other. Yes, and time also very close to each other. Time. Yes, so that you will get a proper heat map diagram. Yes, you can color code that temperature according to a scale. If temperature equal to less than some value, it should be blue. If temperature more than one value, it will be red. So that you can draw how you can know at what time and at what distance the temperature is behaving. Okay, that we will see using Python. Okay, so this idea is something known as FTCS. Okay, that is forward time. We are moving forward in time. T equal to 0, T equal to 1, T equal to 2, so on. Forward time central scheme. Okay, forward time central scheme method. Okay, this is the basic idea for this. So as usual, according to our last understanding, what we should do to a PD always? What we should do to a PD? This is the partial differential equation. How we can solve it? From ODE, you must know this. We always discretize the PDE or ODE. How we can discretize using finite difference? We can discretize the differential equation or partial differential equations using finite difference. Okay, how we can discretize? We have to discretize this equation. We have to discretize this equation. This is the heat equation. Now the question is how we can discretize it. Any ideas? So what you can write dou t by dou t? I told you slope form, nothing else. Slope of 2 points, y2 minus y1 by x2 minus x1. Similarly, temperature at I n plus 1, that is n plus 1th iterate minus temperature I at nth iterate. Okay, divided by delta t. If you like time step difference t2 minus t1, that is the delta t difference, delta t. Okay, how can you write dou 2t by dou x2 based on the previous scheme? Based on the previous scheme, how you can write? How we wrote previously dou 2u by dou x2, left minus 2 times mean plus 2 times right. So t I minus 1 minus 2 times ti plus t I plus 1 divided by delta x squared or h squared, the time step, the step size in the spatial direction. So this is a spatio-temporal dynamics. Can you see spatio-temporal? Most of your geoinformatics students must be using this word, spatio-temporal. Why it is spatio-temporal? On x direction it is changing, that is spatial. Spatial means land, like distance and all those things. What is temporal? With time also it is changing. This solution is changing both in spatial direction as well as in temporal direction. Therefore, it is known as spatio-temporal pattern. Okay, fine. So this, what should be the iterative value at this? That is the question. What value of iterate should you keep? Any ideas? What do you think we should do? We can just use n. We don't have the value at n plus 1, right? What should we keep? N. Why are you so surprised? We should keep n. Like previously I used n. Yes, can you now substitute this? If you substitute, what you get? Tell me. If you substitute this, what you get? Substitute these guys into equation 1. What you get? You have to just substitute and discretize and get a equation that you have to solve numerically again and again iteratively, and you develop the numerical method scheme. So what you get? Substitute and tell me. So what we should write? Ti n plus 1 minus Ti n divided by delta t equals to alpha times Ti minus 1 n minus 2tin plus ti plus 1n divided by delta x squared, right? Now what we should do? What is our aim? Yes, exactly. Our aim is to find the temperature at the next time step. Okay. So tin plus 1 is equal to yes. Hmm? You can take delta t on cross multiply and take tin on the right hand side. So tin plus alpha delta t by delta x squared times ti minus 1n minus 2 tin plus ti plus 1n, isn't it? Agree? Everything on the right hand side is known. Everything is on the previous time step. And tin plus 1 is at the new time step. That's how we arrived at this condition. Fine. You have an analytical solution actually. We don't want to spend time on that. But this is something very nice quantity which you normally see, like this guy over here. This is must be reminding you, those who have already learned about heat equation. How many of you have learned about heat equation? Heat equation? How many of you had PD in your bachelor's? PD. Many of you have had this. You too. Three. Three only. Three. Four. Four people have PD in their class. Yeah, you have. Okay. So, yes. So the idea is, can we solve this? Can we solve this? Can we solve this equation? So you can see, maybe, uh, mm, okay, we will see this in Python and stop it. Huh? Okay, I will tell you one more. I did not say any issue. Anyway, so the idea is simple. I will give you one just problem, like just to make you understand one more small concept, but important one. Like you have this heat equation, that is what we wrote here. Yes, this heat equation 1. Okay. Suppose the temperature at time t equal to 0 is 1. I think, yes. Then the temperature at x equal to 0 is 0. Temperature at x equals to L is 0. Yes. Both the ends the temperature is 0, but at time step t equal to 1. Yeah. Now the idea is simple. If you take the step size delta x to be 0.02 and proceed, the solution converges. Okay. It will get the solutions by numerical method schemes. But the moment you take delta x to be 0.01, solution will diverge. Usually you could have taken 0.01 and solution would have diverged. So this was just an observation which scientists have seen. So this was discovered by Nicholson, okay? And therefore, to avoid this phenomenon, Crank-Nicholson scheme was developed, which will be the one next most important method we will see, okay? So in this method, he used something new to troubleshoot this. So what is the idea you get? What's the idea we get? Based on this step size, some solution is diverging. Based on 0.01, solution is converging. So the solution converges and diverges depending on the step size. It is not always stable. Your numerical method scheme, what you developed here in heat equation, is not always stable. Okay, it is sometimes stable, sometimes not stable. We will derive in the next class when it is stable, when it is not stable. Okay, there we will prove under what condition it is not stable, under what condition it is stable. That will be important. Okay. But can we, now the question is, can we develop a method which is unconditionally stable? Depend, whatever step size you use, however small step size you use, solution will always converge. Therefore, there is a need of another method, which is Crank-Nicolson method. We will discuss in the next class also. So next class, we will solve one heat equation. We will deal with this problem, like how we can solve this problem. We will start from here, then we will progress towards this equation here. Okay. And the second time, like second equation is Crank-Nicolson method. We will understand what Crank-Nicolson method is, how he arrived into his method, how he got the idea of that method. Okay. So nothing, like take average of one thing plus other, and your method will always converge. So we don't know how they got these ideas, but yeah, we still believe these ideas today. And that is Crank-Nicolson method. We will solve one Crank-Nicolson problem also. And I think that will be the end. Okay. Yeah. I think we will meet on Wednesday, no? So after the test, we will continue with the class. Okay. Because Monday is holiday, no? We are 3 weeks behind. Wednesday class, it was not communicated. Test 9 to 10, right? After the test itself. Duration till, we don't know. How much you want? Till we finish it. Wait, one.